Okay, so welcome to week 4, part 2. We're going to take a look at another dynamic programming algorithm here about matrix chain multiplication. So let's dive into this. So let's suppose that we've got three matrices, A, B, and C, and we need to multiply them to get the product ABC. Now, since matrix multiplication is associative, although not commutative, of course, that is, AB is definitely not equal to BA, except in unusual circumstances, we can do this multiplication of A, B, and C in two different ways. We can either multiply A by B first, and then multiply that product by C, or we can multiply B by C first, and then multiply A by that product of B and C. And the question is, do we care? Well, I will hereby confess that in my past life, if I was faced with having to multiply several matrices together, I would just multiply them together from left to right without really thinking about it. But it turns out that it does matter. Okay, so let's suppose that we have two matrices A and B. We're going to multiply those together to get the product of D. Now, each cell in this product matrix D is going to be the result of multiplying a row of A times a column of B. Basically, the dot product of the row of A with the column of B. And of course, therefore, the number of columns in each row of A has to be equal to the number of rows in each column of B in order for this dot product to be well defined. Okay, so as we typically do, we're just going to say, well, A has dimension m by n, B has dimension n by p. We don't really care what those values are as long as they're positive, and we do note that the number of columns of A has to be equal to the number of rows of B. All right. Now, how expensive is it to do this multiplication? Well, we are, as we compute these dot products, we're going to perform n multiplications of the individual item values in A times the corresponding item values in B. And if we just count those multiplications, then we have n operations that we're performing for each cell. We're actually adding all of these things together, so that's roughly another n, but we won't count everything twice. We'll just call this n operations. And since we have m rows and p columns in the result, then the total number of multiplications we're going to have to do is going to be m by n by p. That is the number of rows of A times the number of columns of A times the number of columns of B. Okay, so that is the cost in multiplication terms of doing this computation. To illustrate, let's suppose that we've got this matrix A, and let's suppose that this is 20 rows by 4 columns, and B is 4 rows by 10 columns, and C is 10 rows by 5 columns. So we have the dimensions matching up correctly. 20 by 4, 4 by 10, 10 by 5. So when we compute this product, ABC, we're going to end up with a 20 by 5 matrix when we're all done. Let's suppose that we do compute this thing from left to right. That is, we compute A times B first, and then multiply that product by C. Well, that means that AB is going to require 20 rows times 4 columns times 10 columns of B. That is 800 multiplications to accomplish that matrix multiplication. And if we then multiply by C when we're done, that's going to entail doing another 20 by 10 Okay, the result of multiplying A by B is a 20 by 10 matrix. So that's the result of then multiplying by C is going to be 20 times 10 times 5, the number of columns in C. And we have to add these operations together to get the total number of multiplications that we have to do. So all told, in order to multiply A by B and then multiply that result by C, we end up doing 1,800 multiplies. Alrighty. Well, let's try doing this the other way. Let's multiply B and C first, and then multiply A by that product. The dimensions of the arrays A, B, and C are the same. If we multiply B and C first, then B is 4 rows by 10 columns, and C has 5 columns, so we're going to end up doing 4 times 10 times 5 is 200 multiplies for multiplying B times C. And if we then multiply A times that product, well, A is 20 rows and 4 columns. So we're going to have 20 by 4 times 5 is 400 operations in order to multiply A times the product of BC. Again, we have to add these together to get the total number of multiplications of integers or values, they could be floats, to accomplish A times the quantity BC. But 200 plus 400 is only 600 operations. All right, whereas when we multiplied AB times C, that is, when we multiplied the quantity AB times C, we ended up doing 1,800 operations. So it does turn out to matter quite a lot which order you do your matrix multiplications in. And the more matrices you have involved, the more it matters. Okay. So let's suppose that we've got n matrices, and the dimensions of these things are such that if we write down the product, a sub 1, a sub 2, blah, 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 a sub n, that's well defined. That is, that the number of columns of A1 is equal to the number of rows of A2, and the number of columns of A2 is equal to the number of rows of A3, etc., etc., etc. When we're done doing this product, we get a resulting matrix whose rows are the same as the number of rows in A1, and whose number of columns is the same as the number of columns in AN. We'd like to find an optimal order in which to do this multiplication of this chain of matrices. So, let's do what we always do. We'll do the stupid thing first. We're going to just try every single possible combination and choose the one that has the fewest multiplications, the fewest item-by-item multiplications in it. Well, if we're going to do this brute force approach and just compute every possible combination, we might wonder, how bad is this going to be? How many possible combinations are there in multiplying this sequence of matrices A1 through AN? Okay. So if we only have one matrix, that's nice. We only have one ordering, and in fact, we have 0 operations to do. If we have 2 matrices, there's also only one possible order because, as we said, matrix multiplication is not commutative. So A1, A2 is not the same in general as A2, A1. If we have 3 matrices, though, now we have 2 different possible ways of doing it. We can either multiply A1 times A2 first, and then multiply A3, multiply that product A1, A2 times A3, or we can multiply A2, A3 first, and I just noticed I have a clever typo there. It doesn't matter that much. All right, so we're going to multiply A2 times A3 first, and then multiply A1 times the product of A2 and A3. All right, so things start getting complicated when we get into dealing with 4 matrices. Things start sort of exploding. Now, we can look at this and see how we're going to go about doing it. Notice that for 3 matrices, we had 2 possible orderings. A1, A2 first, followed by A3, or A2, A3 first, with A1 multiplied, and then multiplying A1 times that product of A2, A3. So now that we're adding another matrix, the first thing we're going to do is to get a couple of combinations where we have the 2 different combinations for A1, A2, A3 in front of A4. We're also going to have the same couple of combinations, or the analogous couple of combinations, of A2, A3, A4 with A1 preceding A2, A3, A4. All right? So we've got 2 combinations if A4 is last. We've got 2 combinations if A1 is last. And then we only have one possibility where A1 is grouped with A2 and A3 is grouped with A4. Now here, obviously, it doesn't matter whether we multiply A1 times A2 first, and then multiply A3 times A4, and then multiply the product. Or if we multiply A3 times A4 first, and then multiply A1 times A2, and then multiply the product. We're just counting the total number of item-by-item multiplications we're going to have to do. And so the the order in which we compute A1, A2 versus A3, A4 really doesn't matter. And so now that we've fleshed this out to 4 matrices, we can really see a pattern emerging here, because each time we add another matrix, we're going to have one more case of all of the preceding possibilities with the new matrix stuck on the end, plus one more case of all of the preceding matrices with the new matrix included and the first matrix stuck on the beginning. And then we're going to have all of the sort of middle combinations. So the way this is going to work out, if we think of P sub j as being the number of possible ways of ordering the multiplications of j matrices, well, if we only have one matrix, then there's only one way of ordering it. If we have 2 matrices, there's also only one way of ordering it. We can think of that as being the number of ways of ordering one matrix times the number of ways of ordering the other matrix, right? Because if there's only one way of ordering one matrix, since matrix multiplication is not commutative, if we then have a second matrix, there's only one way of multiplying, there's one way of using the one way of multiplying 2 matrices. Now, when we get to 3 matrices, then as we saw, there were 2 combinations. Because basically we can think of 3 matrices as being one matrix followed by a product of 2 matrices, or 2 matrices followed by one matrix. And then this pattern just continues, so that when we get to some arbitrary number of matrices, the number of operations, or the number of ways of ordering these multiplications, is going to be the number of ways of ordering one matrix times the number of ways of ordering all the remaining n minus 1, or the number of ways of ordering 2 matrices times the number of ways of ordering n minus 2, or 3 matrices times the number of ways of ordering n minus 3, or 4 times the number of ways of ordering n minus 4, blah, 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 all the way up until we get to the number of ways of ordering n minus 1 matrices followed by one matrix. All right, so in other words, we have this sum for k going from 1 up to n minus 1 of p sub k times pn minus k. Now, we've seen something a little bit like this before when we looked at Fibonacci numbers, right? The first Fibonacci number is, well, you know, if we say that Fibonacci number 1 is 0 and Fibonacci number 2 is 1, then all the subsequent Fibonacci numbers are the sum of the previous two Fibonacci numbers. So the third Fibonacci number is 0 plus 1 is 1. The fourth Fibonacci number is 1 plus 1 is 2. This is a similar kind of structure, except that the sum gets more and more complex at each level. So probably you can see that this is going to blow up much faster than the Fibonacci sequence does. In fact, if we extend this idea out to 5 matrices, the number of ways that we can multiply 5 matrices together, now that we know the pattern, is actually fairly easy to just list out. We can multiply A1 times all the possible ways of multiplying we can multiply A1 times all the possible ways of multiplying 5. All right, I was right to begin with. All right, so we can multiply A1 by all the possible ways of multiplying 4 matrices. Or we have all the possible ways of multiplying 4 matrices times A5. Or we have the ways of multiplying 2 matrices there is only one way of multiplying 2 matrices, obviously. Okay, so we have that times the different ways of multiplying 3. And then, of course, we have sort of the mirror image of that, the number of ways of multiplying 3 times the number of ways of multiplying 2. So we just, compute that value and we get 14. And it turns out that this sequence blows up. As I said, it does blow up faster than the Fibonacci sequence by quite a bit. And now I just looked this up. I can't prove it. But so I'm told, this thing grows on the order of 4 to the n. So that's obviously exponential. Pretty bad. And you can see that even if we just get up to just 20 matrices, we've got, what have we got here? We've got almost 2 billion ways of multiplying a sequence of 20 matrices together. All right, so we're just not going to be able to do this. We can't use the brute force approach, which isn't surprising. Pretty much we can never use the brute force approach for other than super trivial problems. So we have to be more clever. All right, so let's think about this in a slightly subtler way. Well, we know that when we multiply a sequence of matrices together, that there is going to be some last multiplication that we perform. Therefore, we can think about splitting up, multiplying the sequence of matrices A1 through AN into multiplying the product of some prefix part times some suffix part. And in order to minimize the cost of doing this matrix multiplication, we know ultimately that we're going to have to do some last multiplication. And in fact, we know exactly what the cost is of doing this last multiplication, because the first factor in the cost is the number of rows of A1. The second factor in the cost is the number of columns of AK, because the prefix is going to have the number of rows in A1 times by the number of columns in AK. Now that means that the number of rows of AK plus 1 has to be the same in order for this multiplication to be well formed. And finally, we have the number of columns of AN. So without knowing anything about the cost of multiplying A1 through AK, and without knowing anything about the cost of multiplying AK plus 1 through AN, we do know that that very last multiplication we have to perform is going to involve the number of rows of A1 times the number of columns of AK times the number of columns of AN. Okay, so just for notation sake, if we have some arbitrary matrix A sub j, we'll use the notation R sub j to indicate the number of rows of that matrix, and the notation C sub j to indicate the number of columns in that matrix. Okay, we don't at this point know what the optimal way is of doing this multiplication, but we do know that when we discover the optimal way, there will be one last multiplication, and that last multiplication will involve that many multiplications. That many multiplications to compute the cells. And lucky for us, there are not 2 billion ways of working out the last multiplication. If there are n matrices, then there are only n minus 1 possible last multiplications that we have to worry about. Okay? That's handy. So if multiplying A1 is the last thing that we do, that's one way. If multiplying A1, A2 by the rest of it, that's another way. All the way up to the n minus 1th way is to multiply all the matrices A1 through AN minus 1 times AN. Whoops. Okay. So now that we know what the cost is of doing that final multiplication, let's define the minimum cost over those n minus 1 multiplications that we have to do. So we'll just define C sub ij as the minimum way of computing some product of matrices from AI up through AJ. Okay? Now, we know that the cost of not multiplying, that is, if I is equal to itself, if I is equal to j, we know that the cost of not doing any multiplying is 0. That's a sort of trivial case that's nevertheless important for bookkeeping. And the minimum cost of multiplying all n matrices together is therefore going to be the minimum of this collection of sums. It's going to be the minimum of either the minimum cost of just multiplying A1 all by itself, which, that's 0, times the cost of multiplying A1 times the product of everything else, times the minimum cost of multiplying everything after A1. All right, so that's one of our n minus 1 possibilities. The second of our n minus 1 possibilities is we can figure out the minimum cost of multiplying A1 times A2, and then we have the known cost of multiplying that product A1, A2 times the minimum cost of the rest of the sequence, A3 up through A sub n, and so on and so forth until we get, our n minus 1th possible cost is the minimum cost of multiplying the first n minus 1 matrices plus the known cost of multiplying that times matrix A sub n, and then in this case, plus 0, because if we only have one matrix, there's no cost involved in multiplying. Okay, so this needs to sink in for you. This is the key to the whole puzzle. You need to agree that C sub 1n, that is the minimum cost of computing A sub 1 times A sub 2 times blah, blah, blah times A sub n, has to be the minimum of one of these n minus 1 possible costs, possible minimum costs. All right, so now if we're going to be able to compute this thing, C sub 1n, that is the minimum cost of computing this product, A1 through AN, we are going to have to compute these prefix and suffix minimum costs as well. In general, for any Cij, the minimum cost for Cij, by the same reasoning that we used to come up with this C1n formulation, the minimum cost of Cij is going to be 0 if I is equal to j. Otherwise, if j is greater than I, we're not going to deal with situations where j is less than I. So otherwise, if j is greater than I, then we're going to need to find the minimum of all of the C sub ik plus the number of rows of matrix I times the number of columns of matrix K, times the number of columns of the final matrix J, plus the minimum cost of the suffix part. And this is going to be true for K going from I up to J minus 1. All right, so it's the same formulation as what we have here on slide 13, just reduced to a smaller interval of matrices from some arbitrary I to some following J. Well, gosh, we're trying to compute C sub ij. That seems very two-dimensional. We've got a matrix I followed later by a matrix J and the matrices in between. So let's put a table together in which we can store theseCijs. And we know that we have n matrices. We're counting the matrices A1, A2, A3 up through AN. So to compute a Cij, we're going to need an n by n matrix. And we'll just fill in the cells here of the minimum cost of multiplying A1 times A1, which is 0, or A1 times A2, or A1 times A2 and then times A3, etc., etc. To add a little bit of concreteness, let's suppose that we have these 6 matrices that we need to multiply. And we've been careful to choose dimensions for the matrices so that this product, A1 through A6, is well defined. Okay, so A1 is 10 by 4, A2 is 4 by 20, A3 is 20 by 8, A4 is 8 by 5, A5 is 5 by 12, A6 is 12 by 3. So in each case, the matrix has the same number of columns as the following matrix has rows. And when we're all done, we're going to end up with a 10 by 3 matrix as the product. Okay? Now, this is not drawn exactly to scale. I sort of, I sort of did my best with the drawing tools. All right. So now let's take a closer look at our matrix that we're going to use to store these values of Cij. We're not going to have any cases. Did I do this upside down? I did this upside down. All right, so in my matrices here, I have I going from 1 to 6 and j going from 1 to 6 downwards. Just pretend that I've flipped the I and the j here for every single one of these diagrams. So the c sub i's go 1 through 6, and the sub j's go 1 through 6, and we're going to not fill in any of this part of the matrix where the I is greater than the j. Okay, so like I said, if you imagine that this is j and this is I, we're only going to fill in values in the matrices in this matrix where the value of j is greater than or equal to I. We can start out by just filling in the cells where we only have one matrix involved. It costs nothing if we're only looking at A1. Okay, there's no cost involved in just having A1. So all of the Cij where I is equal to j, we can just immediately fill all those in with a cost of 0. All right, so that's the simplest step. Now we need to consider all of the Cij's where j is just equal to I plus 1. Okay, and here we can appeal back to our formula here. If we're looking at c sub I comma I plus 1, then, well, it's not 0 because I is not equal to j. I is not equal to I plus 1. And it therefore must be the minimum of all of these possible costs, with k going from I to I plus 1 minus 1, which is I. So, in fact, in order to compute this minimum, there's only one number we need to compute. All right? If we only have two matrices involved, there is only one cost. The cost of the first matrix all by itself is 0. The cost of the second matrix all by itself is 0. And so the only real cost, if we have a sub I and a sub I plus 1 involved, is r sub I times c sub I times c sub j, or times c sub I plus 1. So here's the formula. We're trying to find the maximum of c sub I comma I, which is 0, plus rows in matrix sub I times columns in matrix sub I times columns in matrix sub I plus 1 plus another 0. Okay? Now, these are really easy to compute for each of the possible pairs. All right, so for C sub 1, 2, what we have is 10 times 4 times 20. All right, so 10 times 4 is 40 times 20 is 800. So we get our 800 filled in for C1, 2. For C2, 3, we have 4 times 20 is 80 times 8 is 640. All right, and then for C sub 3 sub 4, we have 20 times 8 is 160 times 5 is 800. And C sub 4 sub 5 is 8 times 5 is 40, times 12 is 480. And then finally, C sub 5 sub 6 is 5 times 12 is 60, times 3 is 180. All right, so again, those are easy to fill in. Now, mechanically, if we're writing code to do this, notice that this number that we're computing here is the sum of C sub 1, which is 0, plus that product, R1, C1, C2, which is 800, plus C sub 2, which is 0. So all that we need in order to compute this cell is the values to its left and the values below it, and the dimensions R1, C1, C2, which are just stored as part of the descriptions of the array variables. All right, and so the importance of remembering about these earlier values in the matrix are going to come into play now when we start taking a look at C sub I, comma, I plus 2. Okay, so here's C sub I, comma, I plus 1. Now, for C sub I, comma, I plus 2, now we have some actual work to do. We're no longer dealing with 2 zeros and a product. We're dealing with C sub I plus rows sub I, column sub I plus 2, plus the cost of I plus 1, comma, I plus 2. Now this time, okay, this guy here is 0, but this is not 0. C sub I plus 1, comma, I plus 2 is definitely not 0. All right, so we have one cost. If we multiply a matrix times the product of two matrices, and we have another cost if we multiply the product of two matrices by one matrix. Okay, so those are the combinations involving three matrices. And once again, we can fill in these numbers from the matrix and doing a simple computation. So for the specific example, C13, notice that C11 is 0. Okay, C11 is 0. Plus rows in A1, columns in A1, columns in A3. So that's 10 by 4 by 8. Okay, 40 times 8 is 320. Plus C sub 2 sub 3. Now C sub 2 sub 3 is this value here. So notice that in my matrix here, my two-dimensional array that's storing the necessary values, I'm looking at C sub 1 sub 1 plus C sub 2 sub 3 plus this product 10 times 4 times 8. So that's going to be 40 times 8 is 320. 320 plus 640 320 plus 640 is 960, just like I have written here. I got myself very confused there for a second. All right, so 320 plus 640 is 960. All right, so that's one of our two possible costs of computing the product A1 times A2 times A3. The other possible cost is going to be C12. The cost of that is 800 plus 10 times 20 times 8. Okay, so the number of rows in A1 times the number of columns in A2 times the number of columns in A3, 10 times 20 times 8, that's going to be 1,600. 1,600 plus 800 is 2,400. And we want the minimum of those two. Well, the minimum of those two is 960. All right, so that's how we fill in our value of 960 there. And let me erase some of this highlighting now so that I can point out important things. That is, in order to get at this value of 960 here, we used 0 plus 640 plus a product of three known values, three known dimensions. We also used 800 plus 0 plus a product of three known dimensions. And then we just took the maximum of those two values, 960 and 2400, and we saw that the minimum cost way of doing this is to multiply come here, is to multiply A2 times A3 first, and then multiply A1 times that product. That way is more efficient, less costly than doing A1 times A2 and then multiplying by A3. Now, we go through that same computational rigmarole for C24, C35, C46, all right? So we need to fill in, whoops, didn't mean to highlight the 800. We need to fill in these, we need to fill in these other diagonal cells. Notice how we're filling this stuff in diagonally. We start with all the CIIs, and then we go to the CI I plus 1s, and then to the CI I plus 2s, and then we're going to do the CI I plus 3, CI I plus 4, CI I plus 5, and in fact, in that case, it's just going to be C1 and C1 comma 6, because we've only got one cell in that diagonal. All right, so here, without going through all the mess, I've filled in these other diagonal columns. Actually, here is another specific example. This is C24. Okay, so that's going to be C22, which is 0, plus the rows in A2 times the columns in A2 times the columns in A4. So that's going to be 4 times 20 times 5. All right, 4 times 20 times 5 is 400, plus the 800 from C sub 3 comma 4. All right, C sub 3 comma 4 is this 800. All right, so we're going to add 400 plus that 800 to get 1,200 as one possible cost, or the other possible cost for multiplying A2 times A3 times A4 is 640, that is C sub 2,3. All right, here's C sub 2,3, that's 640, plus row 2, column 3, column 4. All right, row 2 is 4 times 8 times 5. 4 times 8 times 5 is 160. 160 plus 640 is 800. The minimum of those is 800. All right, so that implies that if we're going to multiply if we're going to multiply A2 times A3 times A4, the minimum cost way of doing that is to multiply A2 times A3 first and then multiply A4. Okay, so that approach is cheaper than multiplying A3 and A4 first, and multiplying A2 times that product, A3, A4. And similarly for C35 and C46. Each time we go along to the next diagonal, our computation gets more complicated. Okay, so for CII, we just had 0. That was easy. Whoop. For CI I plus 1, we only had to compute a value. And of course, the minimum of a value is just the value. And so we were very quickly able to fill in that diagonal. For CI I plus 2, we had to get the minimum of 2 computations. And now for CI I plus 3, we're going to need to get the minimum of 3 computations instead of just 2. Okay, so things are getting more challenging here, but the pattern still holds. We're going to have, in order to get in order to get C14, there are 3 possibilities. We can either ignore A sub 1 to begin with and do it last. We can multiply that times, I'm sorry, we can add that 0 to the rows in A1 times the columns in A1 times the columns in A3. In A4, pardon me. So that's going to be 10 times 4 times 5. 10 times 4 times 5 is just 200. And C sub 2 sub 4, all right, C sub 2 sub 4 is this 800. So 200 plus 800 gives me 1,000. The other possibility, or the second possibility, is C12 plus row 1, column 2, column 4, plus C34. That works out to 2,600. And the third possibility is C13 plus row 1, column 3, column 4, plus C34. I'm sorry, C44, which is 0. And that gets us to 1,360. So, of these 3 choices, the first choice turns out to be the best, and our minimum cost of computing the product of A1, A2, A3, A4 turns out to be 1,000 operations. And we go through similar painful bookkeeping to get 1,400 for C sub 2.5 and 540 for C sub 3.6. All right. This next diagonal, I've just filled these numbers in. Here's the computations that we would have to do. Okay. I just don't want to plug numbers in. I've done this out of PowerPoint. And so those are the values. And so let's get to the grand finale here. Now we're going to get C sub 1, comma 6. And there are 5 numbers that we have to compute now, and we're going to find the minimum of those 5 numbers. So we've got C11 plus R1 C1 C6 plus C26, and C11 and C26 are just right in the table. So C11 is here, C26 is here. All right, so we've got the sum of that number plus this product, 10 times 4 times 3. So that's 120 plus C26. That's going to be 1250. As I wrote down. Okay, so that first number computes to 1250. And we go through the same rigmarole looking up these two values in the table and computing row times column to get 1940. And then we have these two values from the table and row 1, column 3, column 6. That gets us 1600 and so forth. And when we ask for the minimum of these 5 values that we've computed, 1250 is the minimum. And so that's what we fill in. 1250 is the minimum cost in terms of cell by cell multiplications of computing the product A1, A2, A3, A4, A5, A6. Isn't that nice? Okay, so 1250 is the minimum cost. Now, you may recollect that for this example here, where we're looking at C13, that is, I was computing the product of A1 times A2 times A3, and it was pretty easy to deduce from these two computations that we had to do that the lowest cost computation involved using A1 last. Okay? A1 was multiplied by the product A2 times A3. All right? So it was fairly clear what order we should multiply these three matrices in. A1 times the product A2, A3 in order to get this minimum cost of 960. Now, it gets more complicated, obviously, as you get more and more and more arrays involved in your product. And what you have to do is to keep track of the k that you select at each step. Remember that we're multiplying a sub 1 through a sub k, that prefix, times a sub k plus 1 up through a sub n, that suffix. So we're multiplying a prefix times a suffix, and you have to keep track at each step as you compute this diagonal of where the end of the best suffix was. In our case, we know that because we have this computation giving us the best value, the lowest value, the implication here is that we must be multiplying A1 last. All right, so we're multiplying A1 times the lowest cost ordering of A2 times A3 times A4 times A5 times A6. But you have to add to your code the memory of the best ends of the prefixes and suffixes in order to figure out what that parenthesization, what that association of those 5 matrices needs to be. So guess what? You will have to do that. Now, lastly, we've got this algorithm that computes the lowest cost for multiplying these matrices, and this does scale up to an arbitrary number of matrices, but 6 is about the most you can handle in an actual example and have it fit on the page and not put you entirely to sleep. What is the performance of this thing? Well, clearly we've got an n by n array that we're filling values into. We're not filling values into the whole thing. We're only filling values into a little more than half. So we have order n squared just from the two-dimensional array that we're filling in. Is that it? Is it just order n squared? Well, no, unfortunately not, because for each cell that we fill in, there are up to that many values involved that we have to compute, right? So for CII, there was only one value that, we just got the value of 0. For CII plus 1, there were 3 values involved, 0 plus a product of integers. And then for 960, there were, let's see, 1, 2, 3 values twice, if I'm not mistaken. Yes. So 3 values twice. All right, so you can see that the number of values involved in doing each of these computations, is another order n. It's sort of like a loop inside of these nested loops for the rows and the columns, and consequently, the overall performance for this algorithm turns out to be order of n cubed. Alrighty, well, I hope you found that entertaining, and as it probably sounds like, you will be seeing this on your next homework. All right, take care. Bye.